Hello, everyone. On behalf of the Revenue Management Pricing Board, I would like to welcome you to the Revenue Management and Pricing Section Practice Seminar Series. In the 14th installment of our practice seminar series, I'm delighted to introduce my colleagues from the Consumer Pricing Science and Research Group at Amazon. Tara and Joe, they will be talking about the science of pricing experimentation at Amazon. Tara Mardan leads a very dynamic and impactful research group at Amazon, Amazon's Consumer Pricing Science and Research Group. I'm very happy to be part of this group. Her team consists of economists, machine learning scientists, and data engineers who are responsible to design and implement the tools powering pricing for Amazon's online retail business to ensure that the prices for all the Amazon's goods and services are aligned with Amazon's corporate goals. Her team's projects are at the intersection of economic theory, statistical inference, machine learning, and optimization theory. Working for Amazon from 2017, Tara has a PhD in operations research and industrial engineering from University of Minnesota and 15 years of experience in pricing and revenue management field. Joe Cooprider is an economist at the Consumer Pricing Science and Research Group. He graduated with a PhD in economics from Boston College in 2020. His research focused on microeconometric methods, including estimating heterogeneous demand for various products, such as junk food and soda. Joe started work for the consumer pricing research team at Amazon in 2020, where he started working on the pricing labs. And Ozan Can Doğan from University of Chicago Booth is joining us today to moderate the discussion so that we can have a conversation with our speakers. He's an associate professor of operations management at Chicago Booth. He received his PhD and master's degrees in electrical engineering and computer science from MIT. Ozan's main research area is social and economic networks. His research covers two complementary themes. He investigates the impact of networks on operational decisions and also developed novel approaches and tools for the analysis of complex social and economic systems. Ozan will be directing some of the questions you have submitted through our registration survey during the seminar. Please submit any additional questions that you may have using the Q&A function. Tara and I will be collecting them, and at the end of the talk, if we have time, Tara and Joe will try to address some of these questions. Without further ado, I'll leave the floor to Ozan and Tara and Joe.
Thank you so much, Özge, for the introduction, and I would like to thank Özge and our RMP colleagues for putting together this super nice event as well. I am delighted to be the moderator for this event. Experimentation is a super exciting area with growing importance in revenue management, and I'm excited to learn about experimentation at Amazon from Joe, Tara, and our colleagues at Amazon. I know that I'm between you and Joe's talk, so I won't take more of your time. I just have one quick announcement. We will start with the presentation. I think Joe will tell us a little bit about experimentation at Amazon for 30 to 40 minutes. And if you have questions in the meantime, feel free to submit them using the Zoom Q&A function. But one request that we have from you is to label your questions as clarification questions versus discussion questions. Clarification questions, we'll try to relay them during the presentation, and the rest, we'll save them for the end. Time permitting, we'll get to them at the end.
Thanks,
thank you, Tara. With that, Joe, if you can share your slides, we can get started. The floor is yours.
All right, I'll go ahead and get us started here. And are we all good? We're all good?
Yep.
All right. Excited to be here, excited to talk a little bit about this and share some of our work to people outside of Amazon for the first time ever. So this is something that's exciting. Experimentation in Amazon is a big deal. I have this quote from Jeff Bezos that I wanted to start with. To invent, you have to experiment. And if you know in advance that's going to work, it's not an experiment. Most large organizations embrace the idea of invention, but are not willing to suffer the string of failed experiments necessary to get there. So experimentation is obviously very important at Amazon. And so what Pricing Labs is our platform that helps our business partners run pricing experiments and helps them run them easily and get good, accurate estimates, and just try and run them as quickly and easily and help our business partners who don't have a science background run experiments so that we can learn and make better pricing decisions. So the way that my presentation is going to work is I'm going to give you an overall summary of the platform, what it does, what its purpose is, some of the basic problems that we deal with. Then I'm going to talk about some of the science research that we've been working on to improve this. It generally falls in two categories: trying to reduce the noise of our estimates, and then trying to reduce the bias of our estimates, right? So overall, what is pricing hubs, right? We help our business teams measure the causal impact of pricing policy changes. These policies interact, and prices products can be determined by many products over the course of a time. And so we're not trying to measure elasticities. We're trying to measure the effect of switching the policies that we implement to change prices. We do this using typical A/B experiments, and these have to be done at the product level. That's because at Amazon, we don't price discriminate whatsoever. And so if I'm looking at a product and you're looking at a product, no matter where you are, we're going to see the same price if we're looking at it at the same time, no matter what. And we're not going to break that rule for experimentation. And so normally this breaks it down so that normally if you do customer level experiments at a tech company, you're going to have millions of observations. Millions of customers are going to see whatever change you're doing. But in our case, that number shrinks. Our units of observation shrink to about 5,000 to 100,000 products per experiment. Sometimes it's more than that, but that's generally about average. And so this is a lot smaller experiment. These are still large experiments, but a lot smaller than some other tech scenarios. And we generally do about 100 to 200 experiments per year. So we're all on the same page. I'm walking through what a basic A/B experiment is, right? Here we have this example. We have 10 products. Half of them are assigned to treatment, half of them are assigned to control. We have some baseline period for the first 7 days where nothing happens. Then day 8, half the products are assigned to treatment, half the products are assigned to control. And you could just do a simple difference to basically estimate the average treatment effect in this scenario. That's just the basic idea. We're going to talk a little bit more about all the lots of other issues, but that's the basic idea of an A/B experiment. To understand some of the environment around pricing experiments, I have to talk a little bit about pricing policy. Now, I'm not going to talk a lot about pricing policy. If you're here to learn about Amazon pricing policy, you're going to be disappointed because I'm not going to talk about that today. But I do want to talk a little bit to understand a little bit. You have to understand is that our prices fluctuate based on a variety of different factors that can change over time, right? It depends on the MSRP. Now that's not really going to change, but it might depend on costs, which can change based on different things that happen. It can depend on promotions that we're running or our competitors are running. It can depend on prices at other stores, either physical stores or our competitors. It also depend on our inventory levels. And so all of these factors might change, and it also might so that might change the prices of our individual products based on how these change. But also, as these factors change, the policy that is determining the product's price might change. We might switch from one policy that's determined based on inventory levels to another that's based on costs, or another that's based on the prices of other stores, right? So products might get affected by different policies based on other factors outside of our control. And so we built a type of experiment for this called trigger-based experiments, where the scenarios where the group of products that are affected by a policy changes over time. We will choose the products during our experimental period that are affected by the policy or would be affected by the policy during the experimental time. And once it matches the certain criteria such that it would be affected by our treatment, we consider it's triggered. And based on the restrictions of our estimator, we consider once a product is triggered, it is triggered until the end of the experiment. That's a little confusing. So that's, again, why I started with that A/B picture, so we can do a trigger picture to kind of visualize what I'm talking about here. So again, the experiment starts at day 8. And at that point, we have a large group of products, here 10 products, but only 2 match the criteria that they would be affected by our policy that we're testing. And in that case, one of them is assigned to treatment, one of them is assigned to control. And then you continue that on as more products match the criteria such that they would be affected by our policy. They enter the experiment, and once they enter the experiment, they are assigned to either treatment or control. And in the end, we only analyze the experiments that were triggered. So in this case, we'd only analyze the 6 products here, or the 7 products. The 3 products that were not triggered would not be included in the analysis. And this allows us to get a more precise effect of what is the actual effect of our policy, rather than just noisy intent to treat estimators. And so this is something that we're kind of doing, again, trying to just understand. Another sense, this is an example of an issue that we've dealt with that I just kind of want to walk through, because I think it helps illustrate the field that we're in a little bit more, right? Like I said, the people running these experiments are not scientists. They're not economists. They're not statisticians. They're not data scientists. They're normally product managers. And so what that means is that they don't have a good sense of power or a lot of the statistical tools that we need to use to give accurate estimates. And they're often very ambitious about what their policies might do, right? And this is a scenario that we might have where we have a product manager come to us and say, I want to run this experiment. I think this is a really great policy. I think it's going to increase sales 20%. And we say, okay, sure, if you run that, we'll do the power analysis for you. And what do you know? If you're going to increase sales by 20%, you're going to have enough power. You're going to have a significant result about 90% of the time, right? And then they say, great, that's great, we're going to launch it. They launch the experiment, the effect only increases sales by 5%. And then all of a sudden, they're not statistically significant. And they say, wait, you said that I was going to get statistically significant results. Yes, but you also said that your policy was going to increase sales by 20%, right? And so their lack of understanding of the actual effects of what their policies might do leads to the confusion once they actually get the results. And then this can come back around and bite us, because then those people will then say, oh, well, something must be wrong with your product, because I was expecting results like this and the results were not like that. So is there something wrong with your experimentation platform? And so we need to really make sure that they understand what our platform does and does not do. One of the basic ways to do this is to make sure that they actually have good estimates of what the effect of their policies are going to be. And so we've built this simulation service that basically uses historic data to say, hey, if you had implemented this policy in the last month, we know all those factors, the cost of the promotions, the competitor's price, we know all that information for the last month. So given that information, how much would your policy have changed the price? Given a price elasticity service, how would that have changed consumer demand? And then we can get them more accurate estimates of what the effect size is going to be. Then they can have actual accurate estimates of what the power is going to be. And then they can have reasonable expectations. Oh, my power is only 0.5 in this scenario. I need to increase my sample size if I want to actually get statistically significant information. Or maybe I shouldn't rely on statistically significant. Maybe I should rely on a Bayesian framework where I have a lower threshold for success or things like that. And so again, this is what we have to work on, is we have to make sure help our business owners understand the experiments that they're running and understand the results that they're going to get, and make sure that they're actually accurate. We have to make sure that they're actually accurate so we actually are making the right decisions. This is a good break. Do we have any clarification questions?
Actually, one quick question about the simulation service. So
yeah.
I guess the competitors would change their prices in reaction to prices offered by Amazon. How does one account for this in the context of the simulation service that you described?
I don't think I can answer that. We're not going to talk about simulation. I don't think I can answer that.
Okay. I don't see any other clarification questions, so we can continue.
There are going to be some questions that I'm just not able to answer, so I don't think I can answer that question. All right, no other clarification question. All right, let's talk a little bit about some of the steps we use to reduce noise. The first is going to be switchbacks or multiple randomization. At Amazon, we are very lucky to have very smart people working with us. We have Özge working on our team, but we also get to work with a bunch of really smart people that work on other teams. And one of the people that I've gone to work with is Guido Embens, the recent Nobel Prize winner in economics. And he's written a paper on this multiple randomization, helped us with this. What multiple randomization just means is that in addition to just randomizing by products, we can randomize by other things. But for us, in this case, it'll be randomizing by time, such that we're randomizing by products and time, and that will allow us to get a more precise estimate. If we were randomizing just by product A, every single product every day is randomly assigned to treatment or control, this would significantly improve the power of our experiments, because it would allow every product to be exposed to treatment, every product could be exposed to control, so you have a better counterfactual estimates, and it increases the variation for when a treatment starts getting applied. And this, again, at a basic level, you increase the variation of your covariate and you get a more accurate estimate. And so again, if you were to randomize this by product A and there was no bias or anything, this would shrink the standard errors by 60%, which is a huge, much more precise estimator. excuse me. Unfortunately, we can't actually do that because we have this carryover effect that we're really concerned about. The first basic level is that, as I said, some of our prices depend on our competitors' prices. And sometimes it takes us X amount of days or hours to monitor a competitor's price. So if we wait, so if it takes, say, 4 days for us to monitor a competitor price and we change our price won't change until we monitor that competitor's price. And so it'll take 4 days for that policy to be implemented. And so that's a little, so that if we're switching treatment on and off, there's gonna be a lot of the times where there's a delay in it being implemented. And that can obviously bias our estimate of the treatment effect. The second one, I think, is the actual larger issue, is that the effect may change over time. And that if we lower our prices today, we're gonna increase consumer demand today, right? But then when we increase consumer demand, then all of a sudden in search queries, Amazon search queries will say, oh, that product is more popular. Customer is buying the product more. I'm going to put that product higher up in search queries. Or it's going to be more likely to be recommended to customers in the customers also bought section, or all the many different widgets at Amazon. And so there, the next day, when we raise our prices back up, it will still be more prevalent in search queries because it had higher sales yesterday. And so there's this problem where our prices today can affect sales tomorrow. And we've seen evidence of this. And so in the end, we can't really, if we randomize the product day, this will obviously bias our estimates. So again, if we're going back to the kind of graph images that I was looking at before, you've seen this already. This is the typical A/B experiment. Here we have what would be a random days switchback, where every product day is randomly assigned to treatment or control. Again, this would be really good. It shrinks our standard errors by 60%. But again, we have the issue of, like, say, product A, the lower prices in day 8 or 9 would lead to higher sales in day 10 because of the search queries and all these other issues. And that would bias our estimates. And so what we do instead is what we call what's called a crossover. And what that means is that we still have 2 groups, but it's not just a treatment and control group. For the first period, starting in this case in week 7, the first group will be assigned to treatment. And the treatment will be implemented on week 7. And the treatment will go on until week 9. And then in week 10, the treatment for that group will stop and the treatment will begin for the other group. Now, week 7 and week 10 are blacked out because we don't actually measure the impact in those days, because those measurements would be biased by that carryover effect. Instead, we only use the measurements in weeks 8 and 9 and weeks 11 and 12, and along with the baseline period before any of the treatment is applied. And that will actually get us an unbiased estimate of the treatment effect. But again, this gets a lot of the benefits of the product day switchbacks, because not every single product gets assigned to treatment during the experiment, but also every single product gets assigned to control. So we have better counterfactuals as well. And so this gets you a lot more precise estimates, such that this shrinks the standard errors by 40 to 50%. Now, this isn't quite the 60% that we were estimating before, but this gets us a lot of the way there, a lot of the benefits, without the bias of the carryover effect that I was describing. There is a problem in that this cannot be done for trigger-based experiments. So in pricing labs, we still have 2 options, where one is crossover experiments when we know the product population, or triggered experiments where the product population is changing a lot over time. All right, so now I'm at a good breaking point. Do we have any more clarification questions we want to talk about?
There's one question in the chat, but I think we'll take it in the Q&A, and
okay.
I think you can continue.
Okay, we'll continue then. So next we're going to talk about our estimator. We've developed what we call the Heterogeneous Panel Treatment Effect Estimator, HPTE. The main purpose here is a lot of our outcome variables that we care about are customer demand. And there are lots of things that affect customer demand outside of our prices, right? There's our competitors' prices, there's seasonality, there's random commercials that are related. There might be influencers or mommy bloggers or celebrities that might recommend our products. There are many different things that could affect customer demand over time that, outside of our prices, that if we just ignore, are just adding noise to our experiments and basically making all of our estimates really noisy. And so if we can control for some of these factors like seasonality and other customer demand trends, maybe filter out some outliers. I'll talk about why that's really important, and control for some of the differences in treatment and control group that again could add to noise in our estimates. But if we can control for some of these noise, we'll get a much more precise estimate of the average treatment effect estimator, which will allow our business partners to get a more precise estimate of what the effect of their policies are, and then us make better business decisions. So again, there are three basic portions to this. The first one I'm going to talk about, I'll use the example of seasonality. This was the very first experiment that we ran as part of Pricing Labs. This was in the spring of 2019. So Pricing Labs has existed for 3 years now. The very first experiment that we ran. And so we dove deep at this experiment. And the first thing that one of the first things we looked at is, all right, which products had the largest effect of the experiment? And what we found was all of these products were seasonal products, right? All of a sudden, as we go in from late spring to summer, we got a large boost in sales for a fan. We got a large boost in sales for a water float. We got a large boost in sales in toy motors and tie-dye kits. And it's like, okay, these large boost in sales probably had nothing to do with our treatment, nothing to do with our small price change. These things probably had a lot to do with the seasonality. So if we could control for some of these seasonality effects, then we're going to be able to control for a lot of this noise that would make our estimates a little noisy, right? And so what we end up doing is we use the pre-experimental period to estimate a linear trend. And then from that linear trend, we extend that linear trend to the experimental period to basically say, what do we expect to be consumer demand or whatever outcome variable of interest is during the experimental period to be, given the seasonality that we've seen so far. And then once we have that estimate of what we expect the product level demand to be during the experiment, we see how much does the true level of customer demand differ from that. The best way to think about this to me is, again, if you're thinking about a difference, what we normally do is we do post minus pre, where pre is our expectations during the experimental period, right? All right, the average value prior to the implementation of treatment is what we'd expect for the product during the treatment. What we're doing is, instead of post minus pre, we're doing post minus our expected value during the experimental period, given all of the knowledge that we have prior to the experiment. Again, the whole point of HPT is we have tons of data at Amazon. Let's use it to get a more precise estimate of the average treatment effect. And so we're using our pre-experimental data to estimate what we expect the level of consumer demand to be during the experimental period, and taking the difference, the first difference, in our case, what we call the first difference, instead of post minus pre, it's post minus the expected, say, sales during the experimental period, given all the knowledge that we have prior to the experiment. So that's the first step of HPTE. The second step is we got to talk about is this thick tail world.
Joe, before you move on, there are a couple of clarification questions. So one question from the audience is how to deal with very sparse products that have very low transactions. Are there some thresholds for the products to be involved in the experiment?
No. And so this has to be done we'll talk a little bit about that in the next slides. Most of our products are going to be sparse products with what we call low velocity or low sales. And that's just going to be something that we do. If we have enough, then we can generally measure the effect, but that's kind of just something that we have to live with.
Fair enough. Another sounds related question. Is there a realistic number of how many product days are required to identify, say, a 10% increase in KPI as treatment effect? Say if you have 100 products, do you need 1 day, 10 days, 100 days?
It depends completely on how, I'll say the same thing I say to a lot of my product managers who ask me this question. It completely depends on how much, again, I say velocity, or how much sales that product has. If you're dealing with a lot of sparse products, you're going to need thousands and thousands and thousands of those products to be able to actually measure the effect. If you're having a lot of product, if your product's selling on average like 10 a day, then we can measure a 1% effect pretty accurately, right? But if it's selling 0, it's going to be really, and so those questions actually do kind of relate. Right. But generally, for the lower velocity, we generally have to have a larger experiment. For the sparse ASINs, we have to have a larger experiment. But for the higher velocity ASINs, again, we've had some experiments where we've had some of our fastest velocity, and we've had much smaller experiments and been able to tell and get very precise estimates. So it depends a lot on that.
Got it. And another question is related to this slide, the beta I parameter. What does it capture intuitively?
Intuitively, it's just how much during our experiment, at a product level, how much their value differs from our expectations beforehand. How much is it, given the seasonality that we control for, how much does that what is the difference in the true value from what our expectations are?
And related question is about this parameter 65. How do the results depend on it? Can it be tuned? What does that parameter capture?
Yeah, so there's a degree, right, in that the 65 is kind of a balance that we've kind of just found that generally works best for us, but it might not be for most cases and probably could be tuned a little bit more. But there's a balance here in that there's the law of large numbers, where you need at least enough observations so that you can actually estimate the slope of the consumer demand for each product, right? So you need at least 30, right? It's stat 101. Everyone's stat 101. I think the number is generally 30 is that's the number that I remember, is that you need at least 30 in order to estimate, right? So you have to more is obviously better. I don't think you can actually really do 30 in the real world. But you need some more of that. But the issue is if you start getting too many, if you start getting like 120 days, now you're extending 4 months, and seasonality here doesn't really make sense. Like if you extend too many days, then seasonality doesn't really make sense, because you'll capture, like for us, if we started doing 120 days, experiments today would still include like Cyber Monday, which is just, so there's a balance in there. And so generally we've kind of settled that 65 seems to be the best for us, but that's something that you could improve on, I'm sure.
Thank you. These are all the clarification questions. Yeah,
all right, so move on to the next one. Let's talk about fat tails. This is not something I thought about very much in academia, and I kind of scoffed at the idea of outlier treatment, because it was like everything in my soul. I just felt you should treat it, you should include all your observations. But I've weakened on that a little bit, right? So in Amazon, 80% of our sales come from 15% of our products. And so the vast majority of our products are sparse products. They don't have a lot of sales. And so what happens here, now I'm just going to use an extreme example to illustrate this, but if you just have a case where 80% of our sales comes on just 10 of our products, for example, if one of those products has a jump in 10% of its sales because a celebrity recommended it, or some random mommy blogger that was really popular said this is a really good product, then that can significantly influence our estimate of the average treatment effect just from that one product creating a jump. And so I didn't even know about this literature until I got to Amazon, but there's this growing literature, and that even if you're trying to estimate just an average, a sample average, if I was trying to measure the average sales for a product, sometimes in a fat tail world, dropping outliers gives you a more accurate estimate and a more precise estimate than taking the sample average. If you're in a fat tail world, even sometimes dropping outliers gives you a more accurate estimate than just doing a sample, including all of the estimates. I included one of the references, but I think this is something that a part of the literature that I didn't really know. But I think it's really important, because I think in the tech world and at Amazon, this is a real problem. I think that thick tail is the norm, not the exception. I think if we take all of our thin tail methods and apply them to tech, we're going to find out that some of our estimates don't perform as well as we thought they would. And so, so what we end up doing is we create these thresholds that are determined somewhat scientifically, but this is stuff that we're still trying to improve on. But the basic idea is that as our experiment size grows to infinity, the proportions of the experiment that gets dropped as outlier gets trimmed from the outlier goes to 0. So the proportion of products goes to 0, but the number of products also goes to infinity. That's how this threshold is kind of defined. It just depends on the number of products in the experiment. And again, in order to apply this so that it doesn't bias our estimates, we take the high and the low end of both the treatment and the high and the low end of control, so that there's no way that this could bias our estimates. And this seems to work pretty well based on simulations. I'll show some simulation results of all of this put together at the end, but this seems to work pretty well. The last portion of HPT is, again, we want to make sure that our treatment groups are balanced. Randomization does generally make them approximately balanced, and you don't need them to be balanced to get an unbiased estimator. But the more balanced our treatment and control group are, and the more we can control for the differences, the less noise there's going to be. There's going to be less variance in our estimates. And in the end, it also, if we control for any of the differences between treatment and control group, it increases the underlying assumption that the products in the treatment group and the products in the control group would have behaved the same if not for the policy changed, right? And so you want to control for the differences, and that gives you more precise estimates. I use causal force to do this. They're at a basic level, the main reason is just a non-parametric matching. And so it's a non-parametric way to match the differences between treatment and control groups. And so I match based on the product characteristics, like the pre-experimental averages of revenue, profit, page views, all sorts of things like that. When the product is triggered, the consumer demand for the products prior to the experiment. We try and match products on all these characteristics that we can. And then we use the causal force mainly to measure the average treatment effect. I'll talk a little bit about some other uses that we can and we are starting to implement, but for now, that's the main purpose of this, is to non-parametrically balance between all these different metrics to get a more precise estimate of the average treatment effect. My standard errors are estimated by Bootstrap. The Bootstrap is actually really useful here because we often care about more than one metric. We care about revenue, profit, page views, all these different things. And so we can see how those different things interact, right? So we can look at our Bootstrap simulations. We can say, okay, in the Bootstrap simulations where we measured a positive profit effect, what is the effect on page views? On the Bootstrap simulations where we actually see a negative profit, what is the effect on page views in that scenario? And this allows us to basically, allows our business partners to understand a little bit the possible outcomes better. And this allows them to basically kind of view this and say, okay, what's a good case, best case scenario? What's the outcomes? Worst case scenario, what's the outcome? And allows them just to better internalize and better understand the outcomes a little better than plain confidence intervals that are often confusing for people that don't have a statistical background to understand. And again, this is an AA test. I did a lot of simulations, but this is the basic test. And the overall result is using all of these tools, this shrinks our standard errors by about 20 to 30%. And our Bootstrap estimates are a little conservative. So there's always more research to be done and ways to improve. But this does seem to shrink the noise by about 20 to 30% and keeps our estimates pretty accurate. So do we have any, this is a good break. Do we have any comments or questions or clarification questions? Ozan?
I think we are good right now, for now.
Okay, sounds good. So next we're going to talk about reducing bias, cannibalization, and substitutes. Let me take a drink. All right. So I'm going to talk a basic example. I think people have thought about this. I think in this audience, people have thought about this a lot. But just a simple example here. We have two black desks. They're around the same price. So the question is, so imagine we're doing an experiment. One is assigned to treatment, one is assigned control. And in the treatment one, the price is dropped 10%. What will happen is that customers will choose to purchase the cheaper one now, one that isn't treated and had the price drop, instead of the one in the control group. And this obviously violates SUTFA. This is a major problem in that customers in the control group are affected by the treatment, which you never want in your experiment. This will obviously bias your estimates. Numerically, to visualize this again, say we're doing a price drop in the test group, we have all these large increase in units sold, revenue, we even increase profit. But in the control group, we lose 5% of our customers to the products in the test group that had lower sales. And so if we just do the difference, again, basic difference estimate, what we end up saying is, oh, look, our profit increased by 9%, even though in reality, profit actually probably went down. And so if we were trying to make this decision based solely on profit, this would actually lead us to making the wrong decision. And so this it's not a good thing and really problematic. And so this cannibalization, where the growth in sales for the test group cannibalizes from the sales in the control group, is something we don't want to have happen. And so how do we solve this? Well, first thing we need to do is we need to find the substitutes. Now, again, one of the benefits of Amazon is we have a bunch of different science teams doing a lot of different projects. And so we have a bunch of science teams that are working on identifying substitutes. And there's another science team that aggregates all these different science substitute models, and we just eat the aggregated model up from them. In practice, there are two main substitute models that we end up using. The first one says that products are substitutes if they are sold from the same search queries. So again, I have a water bottle here. So if you have two water bottles that always show up with, you say water bottle or plastic water bottle or Nalgene water bottle, and these products always show up next to each other in search queries, then we consider them substitutes. The other scenario is if two customers are if customers regularly look at two products in the same session. If I always look at this water bottle, do I then always look at this water bottle at the same time? And they have to have similar features. Otherwise, you might feel like compliments. But if they have similar features and they're looked at in the same session by customers, they're considered as substitutes. So again, we use the aggregate in that we consider two products as possible substitutes if they are either considered substitutes in the first model or considered substitutes in the second model. And so that's, again, this is important because, again, someone mentioned that what do you do in sparse? If we have a sparse products, which most of our products are sparse, we can't estimate cross-price elasticities. And also we have millions of products. So trying to estimate a million by million cross-price elasticity is just not going to work. And so this is what we end up using to estimate possible substitutes, right? So here's some kind of cluster maps, some possible substitutes. I use a typical in R, it's the greedy clustering algorithm. It's a classic one, but it just basically breaks up some of these larger clusters into smaller clusters. We still keep 99% of the clusters within, or 99% of the substitute pairs within each of these clusters. And so we still get the vast majority of the substitute pairs. And then we'll randomize on these clusters such that we don't have one substitute ASIN that's treated and one substitute ASIN that's in control group. And so that's what we end up doing there. And then in the end, what is the overall effect of this? This does sacrifice our power. We found that this generally decreases our power by about 20%. And that means that we have to increase our sample size by 50% if we want to maintain the same power. And that's a lot of additional products that we need to add to our experiments in order to maintain the same power. And so this is something that we are actually working on right now. This is an ongoing project, but to try and shrink some of these clusters down so that we can maintain much of the same power while still avoiding most of this spillover and cannibalization effect.
A quick clarification question, Joe.
Yeah, that's great. I was going to ask for them.
So interrupt you. Is the pricing policy change identical through all products, given we try to estimate the average treatment effect?
No.
If yes, how is the treatment defined?
So part of the reason of the heterogeneous panel treatment effect, I guess I should have mentioned this, is that we expect the effects to be different. The pricing effects are going to be different, and the effect of the different prices on customers are going to be different. All of these are heterogeneous. We're in a heterogeneous world where the effects of the policies are going to be different on each products. And even if they were uniform, the effect of the price changes would be different on each product based on how the elasticity and other issues are affecting the products.
And other questions, I think we can take it down.
Okay. All right, so I'll just go ahead and wrap up. Those are the main things. I'm going to talk a little bit about what future projects that we're working on as a team. For HPD improvements, we're trying to improve the product trend estimation. Again, I assume a linear trend. There are better ways to do that. And so we're going to move forward and work on better ways to do that. Outlier detection, again, the outlier detection is determined just on the sample size. There are better ways, some literature on adaptive outliers. And so there are more ways to improve that. And then controlling for additional differences between treatment and control groups, something like product embeddings and other things like that we could do to get, again, improve the precision of our average treatment effect estimates. Experimental design improvements, again, I'm part of a group that works with HETO-MBINs, and we're always trying to think about how to improve our experimental design. So improve the trigger-based design, if we can get more precise estimates of the trigger-based effects, and then integrate HPD with crossovers and other things as well. It's already integrated with trigger-based, but continue to integrate HPD and maybe improve crossovers as well. And then the other thing is subgroup analysis. This is something that I think that we're excited about and working on right now, in that you might run an experiment and find that your policy generally has a negative effect, but you might want to try and find which products would it actually have a positive effect if we only applied the policy for this group of products. And so that's one of the advantages of causal force, is it'll be very easy using causal force to point, this is the group of products that the effect is most positive. This is the group of products that the effect is most negative. And so then you could look at that and you could say, okay, this policy launch would be so if we want to launch this policy, it would have a positive effect, but on this group, it's really negative. So we can optimize our policy for that group, or we can not launch it on that group, right? So this allows us to create this allows us to continue the experimentation platform because it allows us to say, maybe you should focus on this group, or maybe you could change your policy for this group. And again, kind of works on the flywheel of where we can then launch more experiments because we're providing more information of where our product managers, where our customers should look for more improvements to the pricing policies. So yeah, just a summary of what we've done. We're a pricing experimentation platform to help our business partners run pricing policy experiments. And our science team, we're working on generally, there are exceptions, there are a few other things. I mentioned the power analysis problem, but broadly our major projects work on reducing the noise and reducing the bias of our estimates. And here I have our names and our emails.
Thank you so much, Joe. This was really interesting. And let me quickly remind the audience that we are going to continue with Q&A. I have already collected some questions. I'll start by asking them. In the meantime, if you think of additional questions, please feel free to utilize the Q&A box. So, Joe, I'll go over some of the questions that I received with you, and I'll start with a very basic question, actually. The question is the following: how many experiments are run each day? I know that you mentioned in the beginning that you are running some like 100 to 200 experiments per year. And I'm assuming these are not all sequential. Perhaps the question is how many experiments are being run in parallel? Like, give us a sense of the scale of the operation.
Yeah, so generally we run about 2 to 5 experiments per week. We're a little bit heavily more sense because we generally don't run experiments during what we call peak season, which is basically Cyber Monday and Christmas and things like that, because those experiments based on our simulations and tests are extremely noisy and extremely likely to get false positives. I can explain that more if you'd like, but generally these 100 to 200 are condensed for the first 9 months of the year. And so again, we get about 2 to 5 a week. And so generally we're filtering them out through that.
That makes sense. And another basic question is about the objective for price experiments. You are experimenting with different policies. What are the metrics you focus on? Do you focus on orders, revenues, profits? How do you think about the trade-off between those in the context of experimentation? And perhaps more fundamental to this talk, depending on the objective, do you tailor the experiment one way or the other?
So I'll take this in 2 parts. I'll answer the second part first. One of the big problems, not problems, but one of the big projects that we have is just that we want to make sure that these experiments can run automatically. I do not want to run 100 to 200 experiments myself. I am not going to do that. We have a platform that allows our business partners to run this without us interfering, or with us just saying, us scanning over a 1-page document to make sure that they actually are running an experiment correctly, right? I mean, we're trying to minimize our effort in here so that we can research all these other things and have time to research all these other things. And so we try to design these things to make sure that they're optimal in measuring the effects for the metrics that were most important. Now, which metrics are most important that we care about the most? I can't answer that precisely, but I will just say generally we care about a combination of all of these, right? We care about sales, we care about profit, we care about page views. If just bringing people to Amazon is always a good thing too. Units sold, these are all things that we care about. How much we care about each of these, I'm not going to say, but we care about all of them.
Okay, makes sense. And another, I guess, related question is, how do you prioritize, size up your projects before taking them on?
I guess I can take that if you don't mind, Joe. So as Joe said, like I think the idea is everyone should be able to test a pricing strategy, pricing idea. We want to facilitate that, but as Joe said, it's impossible to do that given there are many requests and all. So one way that we manage that is in addition to our pricing labs or the experimentation platform that Joe was explaining, which basically is a live experimentation platform. You're exposing our prices to our shoppers. We have some simulation-based mechanisms that basically run these experiments offline. So obviously they won't have the same impact of basically seeing the shoppers or end customers' behavior. but it does give us some idea of how that particular idea may work. So basically there are different stages. At some stage, like with the idea, if not, it's not meaningful, the leadership wouldn't allow it. If it's meaningful, but we don't think like it's worth the cost of like exposing it to our shoppers, then we simulate it offline. And if eventually this is such an important thing or kind of like unknown, exactly what Joe said at the beginning, if we know what is the outcome of an experiment, we won't do it. But if it's so unknown that we don't know and we want to expose it to shoppers, then that's the one that goes to the live experimentation platform.
Thank you, Tara. Joe, there was a question when I guess when you were discussing the cluster based designs, and I'm going to read it to you if you want to add anything extra. So the question says, it's from Shuwan. Looks like a lot of methods talked here make non-interference assumptions, but some products are related. For example, 2 products sold in combo, or 1 product is out of stock, the substitute sales goes up, etc. Can you share your thoughts on that? And the person also says, I think cluster experiment just mentioned is a cure. Is that a cure? Do you want to add something to that?
It's meant to be a cure. We hope it's a cure. This is a difficult issue, right? In that so I'll just say, right, like we have a difficult time measuring the average treatment effect. The average treatment effect is noisy. That's hard. So trying to measure the spillover effect or the cannibalization effects that you often research in academia that are really important, that do actually matter on the aggregate, are extremely hard to measure at the experimental level, or at least the experiments that we do. And so that's why we've kind of focused on the clusters, because it's something that can be automated for any experiment, and it will take away, our hope is, most of these interference and most of these factors.
And I guess a related question is, in addition to cluster designs, what are some ideas for dealing with interference? I guess you also talked about crossover idea earlier. That would be relevant here as well. Yeah,
so there are lots of ways. There are multiple randomization. You could look at multiple randomization, trying to precisely estimate the spillover effect. Ultimately, that's not our goal. Our goal is not to measure the interference effect or spillover effect. That's not something we really care about. We just want to measure the average treatment effect that's unbiased. And so that's why we've kind of focused on clustering, because the sacrifice of clustering is you can't measure the spillover effect or interference because there isn't any. But on the bright side for us is there's not interference or spillover. That's what we actually care about. But yes, and I think there's all sorts of research that could be done about some of this how you could do a better experimental design. But again, part of our work is that we want to create the experiments as simple and as automated as possible, so that we can crank out as many experiments as possible.
That makes a lot of sense. So actually, I had a question related to the challenges that come with the scale. A platform like Amazon is huge in terms of the products, in terms of the users, in terms of the competitors on the platform, and so on and so forth. And I guess, one reason to embrace simplicity might be that. My question is, what are some additional challenges that come with the scale? Are there some algorithmic challenges, for instance, or how does the scale inform or frame your thinking about experimental design?
Yeah, this is a valid issue. We are lucky on our team to work in conjunction with a team of software development engineers. And so we work very closely with them in order to actually be able to run this. And so HPD, I mentioned that there are 3 steps. That is broken up such that each step is run on a different machine, so that we don't run into memory issues, because this is obvious, because on the larger scale, there are real problems in this. And so we've worked very closely with our software development engineers such that, and we did a lot of tests so that we can run this and make sure that the causal force and everything can run even when we have experiments on the high end. Again, I said that our experiments generally are 5,000 to 100,000 products. We have experiments that are 10 million products. And so in those cases, we need to make sure that our products run. So I worked very closely with a team of development engineers, and we're able to make it work. But again, there's a challenge there, right? We've had lots of memory fails, many different memory fails. But again, we're able to break it up, and we'll do one part, get the results, reset all the machines, do another part, and then we're able to get it to work.
I see. Well, additional challenges that come with the size. In the meantime, I see that there are two more questions from the audience, so I'll just relay them. Let me start with the second one from Yimin Yi, who says, do we have a sense of how different methods perform in terms of false positive rate and false negative rate, since we are trying to reduce noise and bias? And this is Yimin's question.
Yeah, I mean, that's a great question. That's always something that we want to make sure, right? False negatives and false positives lead us to launch bad policies, and the bad policies we launch will last for years and cost Amazon millions of dollars. And so this is something that we obviously care a lot about. Now, I don't know what other, so generally we start with the basic estimate. And so what we generally found is that at the basic level, like there's difference to difference, and then there's a regression estimate as well, where instead of assuming parallel trends, you assume, gosh, I'm forgetting what it's called. Anyways, but the moral of the story is whether you're doing that or even a panel difference to difference with two-way fixed effects, all of these provide almost the exact same estimate and almost the exact same level of standard errors. These are all end up basically being about the same. Based on our simulations, like there's some difference, but they most make almost exactly the same. They have the same false positive and false negative rate. In our case, those false positive and false negative rates are about, well, those are actually a little bit less than normal. We're actually below 0.05 because of the randomization technique that we use. Because those they assume there's a literature about this where if you do experiment where when you estimate your standard errors, you assume complete randomness. But if you do a stratified random sample or a bunch random sample, then you're not simple random sample. Your treatment and control group are actually more balanced. And so you're actually even less likely than 0.05 to get a false positive or a false negative. And so that's, yeah.
Let's see. So let me relay another question about heterogeneity. If the treatment is heterogeneous among products, how can we figure out if the heterogeneity found in the effect size is from the heterogeneity in the treatment, something like different effect doses, or the heterogeneity within the product set, let's say based on the product characteristics?
So the cheap answer is we don't know, right? There are lots of answers that we don't know. There's not a ground truth. Ultimately, right, if we can't estimate the heterogeneity using the conditional average treatment effect estimator, that is what causal force is based off of, then our assumption is that it's noise. Now, in practice, it might not be. There might be some other variables that we're missing, and we're always considering adding more variables and more controls. Again, I mentioned product embeddings as a possible example of something that we could use. There are lots of other characteristics, something like elasticity, estimated elasticities for each product. There are lots of different things that we could do where that might not be the case. But generally, our rule of thumb is basically if you can explain it as conditional average treatment effect, then that's where we expect most of our heterogeneity to show up. There's going to be some unobserved heterogeneity, but we're not going to be able to measure that.
Makes sense. Switching gears a little bit, the issues you discussed related to switchback experiments I thought were very interesting. I view these as like non-obvious shortcomings of standard tools that become apparent when you start working on an application. I guess there may be some room for theoretical research related to these, like I guess you use the parameter X, the rate with which the competitors react to price updates. Perhaps one could tune the switchback frequency to account for issues that stem from that. But putting all these aside, I think the fact that when you go to applications, some interesting, non-obvious practical challenges pop up. That is interesting. So what are some novel directions which one needs to extend existing experimentation theory to make it applicable to a platform like Amazon? In your work, have you encountered any practical effects that people haven't thought about, haven't modeled yet, that would be really useful for optimizing and improving your experiments?
Yeah, so there are two broad senses that I think are really interesting. Well, there are three broad ones, right? One is the one that you've talked about, this multiple randomization. Hito Embens has a recent paper that he worked on with some people at Amazon about this, the idea was multiple randomization, but even he's kind of talked about how there's not really any kind of guidance about what you've talked about of how often or how frequent we should switch, how much more benefit are you for switching shorter distance versus longer? Like I don't know of any literature that really outlines that specifically. The other thing is the effect of controlling for variables, even when we randomize. There's some research on that. I looked this up beforehand, the generalized Oaxaca blinder estimator by Guo and Bassi. They have a paper about that, where they look at basically how I think at that point they prove that when you control for variables, will at least be, the standard errors will be smaller or the same size as if you did not control for the variables, given their estimator. I think that's stuff like that is kind of interesting. That's a lot of the stuff that I did with HPTE, but I didn't think there was not actually a lot of literature about that. And then there's another paper that came out a few years ago about panel data and experimental design. And that was interesting in that it showed that the basic takeaway was that adding additional length to your experiments doesn't actually add that much power, which is something that we found to be very true, and that you think that adding a week to your experiment would increase your power by a bunch, but it actually doesn't. And so situations about when that is true and when that's not true, I don't think that there's a lot of detailed research on that. I think is interesting.
Very interesting. And I was looking at my notes. In the meantime, I realized that there was another basic question that we received beforehand, which I forgot to relay.
Okay.
So the question is the following: experimentation can be costly. During an experiment, prices are possibly suboptimal, for instance. When designing experiments, how do you think about these costs? Does this lead to different trade-offs for running experiments involving, for instance, more or less seasonal products? Any thoughts on the cost of experimentation and how to account for that?
Yeah, and so ultimately, I think that kind of relates back to the original quote from Jeff Bezos, in that the larger the possible cost that you're experiencing, it's likely the larger the possible gains. And so you need to be willing to experience the cost, because the costs are going to be for the month that you run the experiment, for the 6 weeks, 8 weeks, for however long your experiment runs for. That's how long you're going to be suffering the costs. But if you end up finding something beneficial, the benefits will last for years, right? In that, like, you choose a policy. If you find that policy A is better than policy B, then you'll run policy A forever. Not only that, but then your next experiment, you'll move in the direction of policy A rather than policy B, and you'll start getting closer to the optimal policy in theory. And as long as you're experimenting and moving in the right direction, then the benefits will almost always outweigh the short run costs of one experiment. That's
just to add to that, I certainly agree with you, but just add to that, there are some costs that we are definitely willing to take, but on the other hand, there are some costs that we are not willing to take, which is the customer, the final shoppers, the customers' trust. So we are not jeopardizing any of this in our experimentation. Not like we are not dwelling on those, but on any other aspect, as Joe mentioned, if we know the experiment is going to be successful or not, there's no point of doing it. So we do take the risk, knowing that it might cause some suboptimal potentially solutions, but controlling for the ultimate impact on the customers, we are not testing on those in our experimentation.
Makes perfect sense. I have 2 questions remaining, and one of them is a quite simple question actually, from the audience. What are some resources you would recommend to people who would like to learn more about experimentation in practice? Any favorite books, textbooks, online courses?
There's a paper that I recommend any scientist that join pricing labs, I have them read, or particularly for economists. I'm not sure if it will be true for us, but it's Econometrics of Randomized Experiments. It's a survey of all the literature written by Athey and Embens. I think it's just a really good summary. That would be my go-to.
Or come to Amazon, work for us. You'll learn a bunch.
It's another good way of picking up the tools, I guess. I know that we are almost out of time. Actually, we're out of time, but I have one final question from the audience that's remaining. So let me just ask it as well in case we have a quick answer to that question. How do pricing experiments interact with with inventory management of the products in the treatment groups? How do you handle stockouts during experiments?
That's a tough question. Generally, our assumption is that they will happen equally in treatment and control group. In reality, that might not affect, but in reality, Amazon has a bunch of inventory management, and we spend a lot of money to make sure inventory management is well done. And so stockouts are rare occurrences, even when we lower the price. But I'll just say that is another thing that is on our list of things to consider in future research topics.
Excellent. So these are all the questions I had and the audience had, and miraculously we are on time. Is there any final words that you would like to add, Joe or Tara?
Go ahead, Tara. I'm good. I'm good. Thank you, everybody.
I don't have any other thing. Just wanted to certainly thank RMP, Özge, and Ozan, you, and everyone who facilitated this this talk for us. Certainly, it's great to be able to connect to our customers. You are all our customers at the end of the day, and explain how these systems work for Amazon. I have 30 seconds allowance to advertise for our team, so I just take the opportunity to do that. If you are interested, or if any of your colleagues and friends and students are interested in learning about these experiments about pricing in Amazon, certainly do reach out to us. We have different type of opportunities, from postdoc to Amazon scholars to full-time employees. So please do reach out to us. We'll be happy to chat with you.
Wonderful. Thanks again, Tara and Joe. It was a delight to learn from you what Amazon is doing on the experimentation side. It's quite fascinating. Thank you for sharing your knowledge with us. And thank you again, Özge, for putting together this webinar.
Thanks, Ozan, for moderating and making this a more lively session. And thanks, Tara and Joe, for this great presentation. We appreciate all of your participation. And thanks to the audience for great questions and for participating to this session. Thank you.
Yeah.
Bye.
Bye.